person actually, if this person makes a donation, or we want to know the probability of this person making a donation. So we have the 4 predictors here: age, we know the age; income, we know the income; employment, we know the employment, it is 100%; and dependence, no dependence, so it is 0. So we have the equation, we have the estimated equation here, and we plug in the numbers for the predictors into the equation, and we use the coefficients that we estimated before. So we can get the coefficients from the results using the $coef. So fit $coef would give us the list of the coefficients, right? So we have the list of the coefficients, we have the values for the predictors for this particular case. We plug in the values and we multiply the coefficients with the values, and we get k equals this. K is the right-hand side. So we calculate k and we obtain k equals 5.71. That means what? That means the log of odds ratio for this person is 5.71. What does that mean? It is positive. So when the log of odds ratio is positive, what does that mean?
There's a higher probability of success
than failure. Exactly, that's correct. So when the log of odds ratio is positive, that means the odds ratio is more than 1, and that means the probability of success is more than 50%. So let's see how much is the probability of success exactly. So what we are going to do is that we are going to just use the formula for the log of odds ratio and inverse it. So we have k as a function of the probability. What we want is the probability as a function of k. So we exponentiate both sides, and then we do some algebra, linear algebra, and we obtain the probability as a function of k. So probability equals e to the k over 1 plus e to the k. The beauty of R is that not only you can put numbers here, you can put just a number here, just 1k here, and obtain the probability for that. You can put a list of numbers here. You can put a list of numbers and obtain the probabilities for those cases. Okay, so keep that in mind. Now let's do this for just this person. K equals 5.7. Therefore, P equals 0.9966 something. So it's very close to 100%. More than 99% chance. So there is more than 99% chance that this person makes a donation. Okay. Now let's look at another example. 52 years old man, blah, blah, blah. So we plug in the numbers, we use the coefficients that we have estimated, and we calculate k. So the coefficients stay the same. We use the same coefficients. The coefficients are from the model. But the numbers, the values for the predictors change. And we plug in the new values for the predictors, and we obtain k equals minus 7.15. What does this mean?
that the likelihood for the donation for the failure is higher than success.
Exactly. That means the log of odds ratio is negative, and that means the odds ratio is less than 1, and that means the probability is less than 50%. The probability of success is less than 50%. So the probability of this person making the donation is less than 50%. But let's see how much it exactly is. can use just the formula, inverse of the log of odds ratio, and obtain P. P is very close to 0. It is 0.000 something. So it is very close to 0%, 0% chance. So we can confidently say that this person will not make a donation. Okay. So we are done with prediction. So now we know how to make a prediction for logistic regression. Okay. Now let's talk about cross-validation. So for cross-validation, the strategy, the main strategy stays the same as the strategy that we had for linear regression. So instead of using all the data up to today, we are going to go back to the past a little bit, and we use part of the data to build the model and estimate the coefficients or train the model. And then we use the rest of the data to test the model. So essentially, we are trying to simulate the future for the model. Because, you know, we are going to use the model to predict the future. We don't want to use the model to predict the past, right? So we want to know about the performance of the model when it tries to predict the future. And to know that, what we do is that we split the data into the past and the future. And the part of the data that the model has not seen is considered the future for the model. The part of the data that the model has not seen yet is considered the future. It is simulating the future for the model. And we call it the test data set. And after we are sure about the performance of the model on the test data set or on a data set that it has not seen before, we can apply it, we can use it to actually predict the future. So there are a few steps for class validation. Then we have logistic regression, just 9 steps, And we just follow these 9 steps to decide if the model is good or not. We can use this model or not, or how good this model is. The first step is splitting the data into the training and the test set. It's exactly like what we did for the multiple linear regression. The next step is building the model or estimating the coefficients using the training set. It is similar to what we did with the multiple linear regression, except instead of LM, we use GLM. And the third step is to classify the observations in the training set into zeros and ones. So remember, in the linear regression, we had the y-hats given to us by the LM function. The y-hats were where were the y-hats? The y-hats were in $ fitted. So $ fitted would give us other y-hat values, right? Here, $ fitted gives us the list of probabilities, the probabilities for the training set. So we have to obtain the classes using the probabilities. How can we do that? We can just use the round function. We round up or down the probabilities into zeros and ones. Of course, we can just use the 50% threshold. Less than 50% means 0, more than 50% means 1. That's how we can actually obtain the classifications for the training set. The next step is to form the confusion matrix. So now we are diverging from the steps for the multiple linear regression. So here we have we have to form the confusion matrix for the training set. So the confusion matrix is nothing but just a matrix that shows the number of correct and incorrect classifications. That's it. So the number of observations that were 0 and were classified as 1, number of observations that were 1 and were classified as 0, number of observations that were 0 and classified as 0, the number of observations that were 1 and classified as 1. So 4 types of classifications. So after we form the confusion matrix for the training set, then we go to the test set. For the test set, we have to calculate the probabilities manually. We don't have the probabilities anymore. We have to calculate them manually. So how can we calculate the probabilities for the data in the test set? It's a prediction problem. We follow the steps. We use the formula that we used before. So at the beginning of the class, how did we do the prediction? We use the coefficients to find the right-hand side k, and then we have k's, and that means we have the log of odds ratios, and then we use the inverse of the log of odds ratios to find the probabilities. And then we use the probabilities to find the zeros and ones. So to find the probabilities, we just use the coefficients and the inverse of the log of odds ratio to find the probabilities. After finding the probabilities, the rest is the same as the training set. We classify the observations into zeros and ones using the round function, and then we form the confusion matrix for the test set. Now we have 2 confusion matrices, one for the test set and one for the training set. We compare them. If they are consistent, they are similar in percentages. They are similar and consistent. That means that the model does as good of a job on the test set as it did on the training set. So the performance of the model is as good as it is in the same level for the test set and the training set. So the performance of the model on the test set is as good as the performance of the model on the training set. And that means the model is consistent and stable, hopefully, if it is the case. If it is not the case, if the performance of the model drops significantly when we apply the model on the test set, that means the model is unstable and we cannot use the model. We have to drop some variables, we have to modify the model or do something. So after we are sure about the consistency of the model, then we can go for the accuracy. We can see how accurate the model is. And the accuracy of the model on the test set would be the accuracy of the model. Okay. So now let's do an example. So first we should divide the data. So the example would be the nonprofit data set, the donation example. So we should divide the data. We should split the data into training and test sets. So which method should we use? How should we split the data for the nonprofit? For the nonprofit data set, a data set that has people, persons, the data points are persons. How should we split the data? The data points are persons. It is not a time series. How should we split the data? So if it was a time series, we would split the data like this. We would just use the first 70% of the data for training, and we use the rest for testing. So we would take the older 70% of the data for training and the later 30% for testing. However, it's not a time series. It's people. So what we do is that we take a random sample. We select a random sample of the data and use it for training. 70% of the data, we take 70% of the data randomly and use it for training, and we use the rest for testing. So this is the size of the sample, 70% times n, and this is all the data. So, so it is similar to what we did for multiple linear regression. Depending on the type of the data set, we choose one method and we split this data into a training and a test set. Good. So after we split the data, then what should we do? We use the training set to build the model. So we use GLM to just run the regression and run the logistic regression and obtain the coefficients. And we have 4 independent variables. We put the independent variables there and we just run the regression model. And at the end, we should put family equals binomial. Just remember that. So after running the regression model, we obtain the coefficients and we obtain something called fitted, $sign fitted. With logistic regression, the fitted would be the list of probabilities for the observations. The list of the probabilities, right? So we have the list of the probabilities. We need to get the zero. We need to get zeros and ones or classes for the training set. So 50% success. So more than 50% is success. Less than 50% will be classified as failure. So if it is more than 0.5, it should be classified as 1. If it is less than 0.5, it should be classified as 0. So you can just use the round function, you know, to do the trick. So now we have zeros and ones. We can easily form the confusion matrix. This is the confusion matrix. We have like 700 observations. So let's say we have 1,000 observations. We use 700 of the observations for training. So these 700 observations will be distributed in 4 cells. Some of them were zeros, and were classified as zeros. Some of them were 1 and were classified as 0. Some of them were 0, were classified as 1. Some of them were 1 and were classified as 1. Right? So this is the confusion matrix. But of course, we prefer to see these cells in percentages instead of just the number of observations. And so let's see what would be the values for the training set. What would be the confusion matrix for the training set? This is the confusion matrix for the training set. We have this percentage or this portion of the data like this. So this cell means the percentage of the data that were actually 0 and were classified as 0. This would be the percentage of the data that were actually 1 and were classified as 1. And this is the percentage of the data, the percentage of the observations that were actually 1 and were classified as 0. This is the percentage of observations that were actually 0 but were classified as 1, right? So the sum of all these 4 cells would be 1 or 100%, correct? The sum of the diagonal elements would be the accuracy of the model, the percentage of the time that the model predicted correctly. classified correctly. So the green cells, the sum of the green cells or the diagonal cells would be the correct classification, the percentage of correct classification. The red cells would be the incorrect classifications. So the sum of the red cells would be the percentage of the time that we classified incorrectly. The sum of the off-diagonal elements or the red cells would be the percentage of the time that we classified incorrectly, erroneously. This is the confusion matrix for the training set. We obtained the confusion matrix for the training set. Now, let's go to the test set. The first step, we need to obtain the probabilities. We cannot obtain the probabilities using fitted. Fitted doesn't work anymore because fitted only gives us the list of the probabilities for the training set. For the test set, we have to manually calculate them. So we just use the coefficients obtained from the training set, from the model, and calculate the K values for all the observations in the test set. And then use this formula to obtain the probabilities for the observations in the test set. So the beauty of R is that we can just put the list of K's in this formula and we would get the list of probabilities. So that makes things much easier. And after that, the next step is that after we obtain the probabilities, the next step is similar to what we did with the training set. Now that we have the probabilities, we just need to round up or down the probabilities into zeros and ones. More than 50% will be classified as success. Less than 50% should be classified as failure, right? And we can use the round function to do the trick. So now we have the zeros and ones, the predicted zeros and ones. We can compare the predicted values to the actual values. Of course, we have the actual values for the dependent value. So we can make the confusion matrix for the test set. This is the confusion matrix for the test set. Very similar to the confusion matrix that we had for the training set. So now we have to judge the consistency and stability of the model. So how would you compare the performance of these two data sets, the training data set and test data set? You compare the confusion matrices. And the confusion matrices are very similar. As you can see, it's about 95% chance that one would be classified as one in both cases, on both data sets. If it is one, there is about 0.6% chance to be classified as zero in both cases. And if it is zero, it is 2 and 2.7, about 2.7 chance to be classified as one in the training set and in the test set. You can see the elements are very close to each other. So we can safely say that this model is consistent and stable. When we apply the model on the training set, its performance is something. And then we apply the model on another set that it has not seen before, let's call it the test set, its performance is similar. Its performance does not drop. So that means the model is stable. Stability means that the performance of the model is almost the same on different data sets. Good? Okay. So we judge the model as stable and consistent. Now we should judge the accuracy of the model. Now that the model is consistent, For accuracy, we look at the test set. And we see what percentage of the time we classified correctly and what percentage of the time we classified incorrectly. So you can add up diagonal elements and see that we classify correctly 96.6% of the time. And you add up the off diagonal elements and you see that we classified incorrectly 3.4% of the time. Right? Any question? Any questions so far? Are we good? So we are done with cross-validation and prediction for linear regression and for logistic regression. So I'm going to show you an interesting example. Let's talk about an interesting example of a classifier, a specific classifier. You are a classifier as a researcher. So when you face a null hypothesis, you have to classify it as true or false, right? So if the null hypothesis is false in reality, that means we have a significant effect. And you reject the null hypothesis. You correctly reject the null hypothesis. That means what? You could detect a true effect, a real effect, a significant effect. The probability of that would be 1 minus beta, and it is your statistical power. However, what if the null hypothesis is false? And we mistakenly accept it. We accept the null hypothesis, even though it is false. What type of error are we making? So the null hypothesis is false. That means there is a relationship there. There is an effect there. But we accept the null hypothesis. We cannot reject it. We fail to reject it. That means we failed to detect a real relationship. We failed to detect an actual relationship. That means type 2 error. The probability of type 2 error is beta. However, if the null hypothesis is true, there is no relationship. But we mistakenly reject the null hypothesis and conclude that there is a relationship. We are making type 1 error. Error type 1 is rejecting the null hypothesis by mistake. Its probability is alpha, right? So this is the confusion matrix for a confused researcher. So when we are confused, that's our confusion matrix. So, any question? Any question? Okay, let's go to R. Before that, I should mention that tomorrow I'm making a presentation in the political science department. If you like, you can attend. It's not much related to business analytics, but it's related to economics. So you can attend if you like. It's in Gore 320. Gore building is just across the street, and it starts at noon. So let's open our studio. Okay. We are going to just do the same example that I showed, nonprofit. When I try to read the file, it gives me an error. That means I should change the working directory. The correct working directory would be course data. And now I try to open the file again. Open the file. And we have these columns as before. So how many observations do we have? The length of one of the columns, any column, would be the number of observations, the number of rows. So we have 11,254 rows for observations. Now we should split the data. Since it is not a time series, we should randomly select 70% of the data and use it for training. So we use the sample function to randomly select 70% of the data. So train equals sample of 1 to n, comma 0.7 times n, the size of the sample, comma replace equals false, no duplicate. Then we use the rest of that for testing. So we use the setDiff function, which is like just minus. So 1 to n minus the training set. So we get the test set. Not the test set, actually it's the indices for the test set. The train is the indices for the training set. To get the actual test set and the training set, we just use the indices on the data frame, in the data frame, and obtain that portion of the data frame. So D of train would be that portion of the data frame that we use for training, D train. And D of test would be that portion of the data frame that we use for testing. So far so good. So we have two data sets, D train and D test. To run the model, so the second step is just running the model and building the model or estimating the coefficients. Use GLM, the GLM function. First, we have the dependent variable. So with the data set, $, the variable name, then tilde, the names of the other variables. So data set, $, the name of the first predictor, the second predictor, the next predictor, next predictor. And then at the end, we put family equals binomial to indicate logistic regression. We are talking about logistic regression. So as you can see, we are repeating the data frame just here, the name of the data frame before each variable. In most cases, we use the same data frame for all the variables. So all the variables are taken from one data frame. As you can see in this case, it is the training, right? So what we can do is that we can just put the names of the variables here, as you can see, and we put another parameter that is like this, data equals the train. And here we specify the data frame for all the variables. See, data equals the train. This parameter specifies the data frame for all the variables, And we don't need to repeat this $sign again and again. So this command is equivalent to this command, almost equivalent to this command. So these two commands are almost equivalent, except this one is a little bit shorter, you see? So we run this, it gives us the results, we can run this, and it will give us the results, the same results. So we can see the results using summary. As you can see, all the coefficients are significant, including the intercept. So all the 4 coefficients and the intercept are significant. 3 stars for each one. In addition to the coefficients, we get the fitted values. We can just obtain the fitted values using $sign fitted or the y-hats. These are the y-hats. In the case of the logistic regression, the y-hats are actually what? The probabilities. The fitted would give us the probabilities. So we have the probabilities here. We want to convert the probabilities into classifications, zeros and ones. So we can do what? We can just use round with 0 decimals. It's 0 decimals to give us 0 and 1. No decimal, 0 and 1. So the probabilities are between 0 and 1. They would be just classified into zeros and ones. So round of fitted the probabilities with 0 precision. So we have training. This way we have training predicted values. The predicted values for training. Like this. Now we have zeros and ones. Instead of probabilities, we have the zeros and ones here. That's what we need. So the actual values are here in the data set. Donation binary. They are the actual values. We already have the actual values, the y's, the dependent variable. So that's the actual values. So we have the actual values here. Okay, can just make it a little bit clear that still no. Yeah, the actual values also are zeros and ones. So now for each observation, we can decide in which cell it should land. If it was 0, but was predicted to be 1. If it was 1, was predicted to be 0, was 0, you know. So we can form the confusion matrix now. We have the actual zeros and ones and predicted zeros and ones. So to form the confusion matrix, you can just sum up the zeros and ones like that for the probabilities. So you can just count the number of observations in each cell and then manually just form the confusion matrix, or you can just use the aggregate function to do all at once. So just as a reminder, the aggregate function would give us the would apply a function on some list. In this case, we are applying the function length on a list, on this list. Since it is the function length, it would just give us the number of elements or the number of rows, the number of observations. That means the content of this list doesn't matter. If it was average, sum, variance, whatever, the content of the list would be important. But now it is length, so just the number of rows matter. So we can use any of the lists here as long as the list has the same length as the training set. You know, so use train prediction or train actual, either one would work. So aggregate some list, and then we have y. So how do we section it? How do we group by the list? 2 variables, training prediction and training actual. So the first variable has 0 and 1. The second variable has 0 and 1. So the combination of them have 4. The combination of them has 4 possibilities. The combination of them has 4 possibilities: 0, 0, 1, 1, 0, 1, 1, 0. So essentially we have 4 subgroups, and we just want to length of each subgroup. That means the number of observations in each subgroup. That's the confusion matrix, right? So we run this command, aggregate, and we get this thing that is very ugly because we don't know what is group, what is X. So we rename the columns using the column names, call names, to make it prettier. So the call names for this data frame, the output of aggregate would be a data frame. The call names for this data frame will be training prediction, training actual, and count, the number of observations in each group. So we have that, and then the confusion matrix would be like this, or not yet. Instead of count, we prefer to have percentages. So that's easy. How do we obtain the percentages? The count for each one, for each group, just divided by the total count. The total count would be the sum of the elements in the third column. So each element is divided by the sum of the elements, and then multiplied by 100 to give us the percentages. So we have that. So I replace the counts with the percentages. Now I have to rename the columns, rename the last column to percentage. I rename it to percentage, and I have the confusion matrix, the final confusion matrix for a training set. This is the confusion matrix for a training set, right? We know the percentage of observations under each category. Correct classification or misclassification. So now what should we do? We should find the confusion matrix for the test set. To find the confusion matrix for the test set, first we need to find the case. The case for all the observations in the test set. To do that, first we get the values for the predictors. Put the values for the predictors in x1 to x4. So the predictors are age, household income, percentage employment, household dependence, 4 predictors. Just for easier handling, we put them into x1 to x4. Assign them to x1 to x4. So our predictors are x1 to x4 now. We already have the coefficients from the training set because we already built the model. So the coefficients are estimated using the training set. Now we apply the coefficients on the data that we have from the test set, the predictors from the test set, x1 to x4. So the estimated equation is like this. And we calculate the k's like this. So we have the k values for all the observations in the test set using this formula, the estimated equation, right? The estimated equation one. It is a prediction problem. Very straightforward. So when we have the k values, we can obtain the probabilities. We just use the inverse of the log of odds ratio, this formula. So we put the k values, the list of k values into this formula, and we get the list of probabilities. And the list of probabilities would be like this. These are just the first 5 probabilities. So now the rest is similar to what we did for the training set. We should just classify the observations based on their probabilities. We have their probabilities. We should just use the round function to classify the probabilities into zeros and ones. So that's the trick that we use. And we have the test prediction, zeros and ones. So we have the predicted values for the test set. The actual values, we already have them, at least in our data set, donation binary. So we have the actual values, the actual zeros and ones, and the predicted zeros and ones for the test set. That means we have the confusion matrix. We should just form the confusion matrix. So again, we should just group by test predicted and test actual, zeros and ones. And we apply the function length, and the list that we use is test region. So use the aggregate function to form the confusion matrix. We rename the columns just in case to make it prettier. So the confusion matrix would look like this. Not completely, it's just the confusion matrix with the number of observations instead of percentages, right? So to get the percentages, we divide each element by the sum of the elements and multiply by 100. So just this formula. And of course, we have to rename the last column to percentage because the last column was count. Now it is percentage. So we rename the last column percentage using call names. And we have the final confusion matrix for the test set in percentages. Good. So you might have noticed that the percentage here is slightly lower than what we observed before when I was showing you the PowerPoints. Why? Why would that happen? So remember, when we split the data set into a test set and a training set, we use random sampling. Each time that we do the random sampling, we take a different part of the data. Therefore, each time that we run the model and form the confusion matrices, we get slightly different numbers, right? Slightly different numbers. So now let's see how accurate the training set was. So the diagonal elements in the confusion matrix are what? The percentage for 0, 0 and the percentage for 1, 1. We sum up these two percentages and we get the accuracy of the model. So for the training set, would be this, 96.6. For the test set, again, we sum up the diagonal elements and we get this, 96.62. So very close, very close. And that means the performance of the model on the training set is the same as the performance of the model on any other set, right? So the performance of the model does not change when we move from the training set to another set. And that means the model is stable and consistent. That means we can use the model to predict the future. That would be the purpose of the model. So now that we saw that the model is consistent, we can talk about the accuracy of the model. The accuracy of the model is the accuracy of the model on the test set, which is 96.62%. Right? This is the accuracy of the model. So, any question? So you have access to this script. It is already in the module for prediction. So in the prediction module in Canvas. So we have time. That's interesting. Oh, there is one more thing that I wanted to mention. The classification that we saw, or the confusion matrix that we saw, is the simplest case for classification, classifying true and falses into true and falses. So success and failure into success and failure, 0 and 1s into 0 and 1s. So that would be the simplest case, but in general, classification can be more complex. We can have multiple values. We may have a categorical variable as the dependent variable. Of course, we cannot use logistic regression anymore. We can use other methods like random forest or neural networks, but still we would have a confusion matrix. But the confusion matrix would not be 2 by 2. It would be m by n, the number of classes, based on the number of classes. Let's say we have an image processing problem, and we have pictures of animals, and we want to classify the animals into the correct kind of animal. We want to classify each animal into the correct kind. We want to detect which animal we see in the picture. So we will have a matrix like this. Let's say we have 6 animals: cat, dog, horse, bear, monkey, fish. Okay, so the actual animals, we know the actual animals in the pictures. Okay, we use the model to classify the animals. We train the model first, of course, and then we want to classify the animals classify the pictures into animals. Then we classify each picture into cat, dog, horse, bear, monkey, or fish, right? So this would be the confusion matrix, 6 by 6, because we have 6 classes, right? So the diagonal elements are the correct classification measures, the correct classification percentages. So the sum of the diagonal elements would be the accuracy of the model, of course, for the test set. So when we apply it for the test set, the confusion metric for the test set, in the confusion metric for matrix for the test set, the sum of the diagonal elements would be the accuracy of the model. That means the trace of the matrix. The trace of the matrix, the trace of the confusion matrix would be the accuracy of the model. That's it. So we should know that the rows are the actual classes and the columns are the predicted classes. Okay. Off diagonal elements are the misclassification percentages. So what percentage of dogs were classified as monkeys? What percentage of monkeys were classified as cats? What percentage of monkeys were classified as fish? You know? But the diagonal elements are the correct classification measures, the correct classification percentages. Good. So this is the general confusion matrix for general classification problem. So now let's do an example together. So we had another example with